Okay, so now we are starting chapter 20, which is about magnetism. You must all have played with magnets in your life. Now, it's a lot of fun. And you may have realized that depending if you bring two magnets together, depending on how you bring them together, they either attract each other or repel each other. And how we explain that? We say that on each magnet, each individual magnet, we have two sides, and we call these two sides two poles. One we say is the north pole, and the other one is the south pole. So these are just names. And as we bring the two magnets, each magnet has the north and the south pole. If we bring these two magnets close to each other, but we put them close, the north side of each one close together, then they will be repelling each other. If we put the south poles together, they will repel each other. They only attract when we have the south and the north together. Anyway, this idea of attraction and repulsion reminds us of what we saw about charges. When we put two positive charges together, for example, they repel, positive and negative attract. Again, these positive and negative are names. This north and south pole for the magnets are names. But what is the main difference between the magnets and charges? In the case of charge, they are isolated. They are either just positive or either just negative. In the case of the magnet, each magnet, they always come with both poles. Okay, so this is what this drawing is trying to show. If I have this big magnet and if I break it in two, well, again, these new two pieces will have the south and the north. And if I break again, each piece will have the south and the north. We can never get a monopole, just the north alone, just the south alone. It always comes in two. And the question is then, where is this force coming from? Well, similar to what we talked about charge, what we said that a positive charge, let's say a positive charge Q, creates around it an electric field. Now in this case, the vectors for the electric field are pointing away, as we talked. Okay, so if I now bring another charge, another little Q here, this little Q will feel a force. Now, even though it's not in contact with the big Q, it will feel a force through this electric field. So the force that this little Q will feel is that proportional to the electric field of the big Q. Okay. Anyway, all that to say that around the charges we have electric fields. That was the subject in chapter 16. Well, around magnets, what we are going to say now is that we have magnetic fields. Okay, and this is what you see in this other slide. Here we have a magnet, the north and the south. So again, by convention, we choose to say that we have magnetic fields around. This magnetic field is a vector. And what is the direction of the vector? Well, the convention is to say that it leaves the north pole and goes to the south pole. Leaves the north pole and goes to the south pole. In my drawing here, north is here, right? So it leaves the north and goes to the south. So this is the direction of the magnetic field. So all around here, we have these vectors representing this magnetic field around the magnet. Okay, so let's come back to our first slide. Well, we talked about the magnet. We say that it has a magnetic field around, but still, what is the origin of this thing, these magnetic fields? We talk about the spins of the particles, especially the spins of the electrons in this case when we are talking about magnetism. What is spin? You can see, well, any elementary particle, they have a certain spin. Like we say that the electron has a spin half. The proton, the neutron, they also have spins half. These elementary particles, the constitute matter, they have spin half. And what is a spin? Well, you can look at each tiny, each electron as if itself was a tiny magnet. Okay. Now, when we have a certain material and at a certain temperature, let's say room temperature, each one of the electrons in this material, they are pointing in a certain direction. And so these arrows that I'm representing is like these little magnets with a north and south direction. Okay, so we have all of these tiny magnets, each one in one direction. So the net magnetic field, so each tiny electron is as behaves as a magnetic field, but since in this material they all point in arbitrary directions, the net magnetic field, and I'm going to indicate magnetic field with the letter B, the net magnetic field of this material is just zero. Okay, so this is the magnitude of the magnetic field. So this piece, this material that I'm looking at, is not going to behave as a magnet. Well, what happens in permanent magnet? There are some examples in nature of permanent magnets, like the lodestone, which is a permanent magnet found in nature. What makes it a permanent magnet? Well, these pins there, they are all pointing in the same direction. So we have all these tiny magnets all aligned, and as a result, their sum creates a net big magnetic field. So it behaves as a macroscopic magnet with properties that we can notice by playing with them. There are other kinds of materials which we call ferromagnets, which are not permanent magnets, but they can behave as a magnet. How? So what are the examples of ferromagnets? You see here iron is an example, nickel is an example. What it means. So if I pick a piece of iron by itself, it's not going to behave as a magnet. But if I put this piece of iron close to something, to a big magnetic field, what is going to happen is the electrons inside this piece of iron, they will get the spins of this electron will get aligned with the magnetic field, easily aligned. And so this piece of iron now creates itself, gives rise itself to a new net magnetic field. So now this piece of iron can behave as a magnet. Okay. Now, if I take this piece of iron away from the magnetic field, well, if you wait some time, eventually you will have the spins pointing in arbitrary directions again, so you'll see that this magnetic field will die away. Okay, but so these materials that are easily magnetized, we put it close to a magnetic field, and the spins of these electrons get all aligned, and therefore we get a net magnetic field. They're called ferromagnets. Okay, all right. So let's continue with our story here. So one way to have a magnetic field is through a magnet. So we have here north and south. Now this is my piece of magnet, so around it I have magnetic fields. What is this magnetic field? Well, what is the consequence of this magnetic field? Now, if I bring close to this magnet another magnet, it will feel attracted. For example, if I put in this way, even though the two magnets, they are not touching each other, because of these magnetic fields, this other magnet that I brought close will detect this magnetic field, will have and this will generate a force between the two. Okay, this is one way to create a magnetic field via a magnet. There is another way to create a magnetic field, which is once we have current, flow of charge, this creates around it also a magnetic field. So another way to create magnetic field is by having charges in motion. Okay, so how we have a magnetic field around the magnet, we have magnetic field. This is one source of magnetic field, but charge in motion is another source of magnetic field. Okay, All right, all this to tell you about something that is very interesting. Earth, planet Earth itself, behaves as a big magnet. Now, so around Earth, we have this shield of magnetic field. And where is this magnetic field coming from? Now, what causes the magnetic field around Earth? The story is, if you go inside Earth, well, if you go deep, deep inside, there is that center, the nucleus that is solid, but around it, so inside Earth, deep inside Earth, below the surface, there is a region that is very, very hot, and where we have some like a plasma, where we have ions. And these ions, they are moving through convection. So ions are charged elements, no? And they are moving by convection. So we have like this flow of charged particles, and this creates a magnetic field. This creates the magnetic field around Earth. Okay, what are these charged? They are mostly iron, no? Ionized, creates this magnetic field. Now, the interesting thing also is that the magnetic field around Earth is not permanent. Well, it is permanent, but the direction of this field is not always the same. It changes. It takes a very long time, millions of years, but it changes. As it is nowadays in our lives, uh, do how do these magnetic fields look like? So here you have this picture of Earth. This top here is what we call the north geographic pole, and here at the bottom the south um, geographic pole. So here at the top, where we have the closer to Canada, and here at the bottom close to um, South America, New Zealand, Argentina, and Chile. Yeah. Anyway, so this top is what we call the north geographic pole, and the bottom here, the south geographic pole. Now let's talk about magnetism. If we talk about magnetism, this magnetic field around Earth, the north magnetic pole, not the geographic, but the north magnetic pole is here, where you see this N. Okay, and the south magnetic pole is here. Okay, so what are we seeing? That the south magnetic pole of Earth is close to the north geographic pole. And then you say, what the heck? Why did they decide to make this mess? Well, because how do we talk about the geographic north or the geographic south? We use a compass, isn't it? And what is the compass? On the compass, we have this needle. This needle is itself a magnet. Okay? So the north pole of the needle points towards the south magnetic pole of Earth, no? Because the north is attracted by the south. So when we talk about the north geographic pole, we have in mind where the compass needle is pointing towards. Okay? So there is this little funny confusion. Now, the north geographic pole does not coincide exactly with the south magnetic pole. They are close, but there is a little difference, and this little difference is corrected in all the instruments for navigation that we have. Okay, but again, coming back to this story, this is how things are at the moment. This exact direction of the big magnet of Earth can change in time. But it takes a very, very long time. And how do people know about that? By studying the rocks, by studying these features that will tell you what was the direction of the magnetic field on Earth. And in the future, again, it can change. This magnetic field that we have around Earth is very useful for us. It behaves as a shield against attacks of charges that come from out space. And This is what I'm trying to show to you in with some videos in these slides. The main attack comes from the sun. Now, in the sun, we have some explosions, and when we have these explosions, the sun sends out in space charged particles. Now, these are called solar winds, and they come towards Earth. And what would be the big bad effect of these charge? They can damage our electronic devices. Now, so you can lose electricity. There are examples of big solar winds that left cities without electricity, especially, for example, in Canada. But because of this shield, we not all of this, most of these charged particles actually do not penetrate Earth. When these charges are coming from the sun, once they reach these magnetic fields, they spiral, and either they fly away, they are lost in space, or those who manage to penetrate Earth, most of them penetrate Earth in the poles, the South Pole or the North Pole. When these charges come and penetrate Earth, they come with a lot of energy, and they collide against the molecules in the air, excite these molecules for a while, but then once they lose this excess of energy, that's when we get radiation. That's when we get what is known as aurora borealis, or aurora australis, which is the one that happens in the South Pole. Another name for the aurora borealis is the northern lights. So people from Canada may have seen it, which is this beautiful effects in the atmosphere. What is the cause? These explosions that are coming, the solar winds, these charged particles that are coming from the sun. So they are coming because we are shielded. Many of them will be lost in space, but those that manage to penetrate, excite the molecules in the air, which would then cause those beautiful effects. The color of the aurora depends on the elements that are being excited there in the atmosphere. Okay, so these topics are beautiful. I'm not going to give you many more details, but I put you sites here, and I hope you're going to watch. Now, so this site here is explaining to us about the origin of the magnetic field around Earth. So watch this. It's a very interesting video. There is this other one which is talking about the solar winds, and then this one explaining about the aurora, the origin of the aurora. So I really hope you're going to watch all these things. So this is the end for this introduction. We are going to continue in the next lecture talking about the magnetic fields created by current.